Hello everyone, today I will present our work, FSLens, a visual analytics approach to evaluating and optimizing the spatial layout of fire stations. As we know, fire poses a threat to our life, property, and even the environment. In our cities, fire stations are responsible for fighting fires. The rescue in Fisher had a direct impact on damage and casualties. Of course, this infrastructure is closely related to the layout of the fire stations. For example, if there is a fire station every 1 kilometer, then I believe that any fire can be responded to very quickly. However, the reality is that firefighting resources are limited. Therefore, it is very important to evaluate and optimize the existing layout of fire stations. There are many previous studies on this. The earliest studies were usually based on the location set coupling problem, aiming to get the largest possible coverage. Considering the complex of the reality, later researchers introduced more criteria to determine the location. They also used the geographical information system as an aid. While these approaches have been proved effective in particular scenarios, they still have some limitations. On the one hand, planning based on multiple criteria often lacks interpretability. For example, it's not easy to know which criterion plays a more important role in location generation. In addition, there may be potential conflicts between the criteria, which can lead to no unique optimal solution. On the other hand, most of the traditional methods place multiple fire stations uniformly over a large geographical area. This may encounter limitations when dealing with large data. To improve these shortcomings, we combined visual analytics techniques with traditional methods and proposed FSLens. In the initial design phase, we worked closely with experts from the fire department and partner university to summarize their workflow in practice, from which we derived a set of requirements. Based on this requirement, we extended the familiar visualization metaphor. First, the statistic overview allows the user to load datasets from different cities with corresponding statistical information on fire indicates and fire station conditions. The fire service supply and demand will check changes in the number and the response time of fires over time, providing insights into factors influencing fire occurrence based on the forecasting module. In this view, the upper step-line chart indicates the fire number and the influencing factors. We hope to reveal potential fire occurrence patterns through it. Specifically, we use the spatial tempo sequence forecasting methods. The entire urban area is first divided into equally sized grids. Then five time-varying features are assigned to each grid and counted at fixed intervals. Finally, the input data is passed through a deep learning module to get the predicted values. To enhance the interpretability, we also visualized the effect of different features on the predicted values using stacked bar. We can see that the color of the bar is used to mark different features, and its height is positively correlated with the shape value. The lower subplot demonstrates the distribution of response times taken by fire stations to reach fire seasons. The spatial tempo view employs a map-based exploration method to exhibit the distribution of fire indicates and the layout of fire stations. In this view, we used hierarchical grid layer to depict the spatial distribution of fire indicates. At the lower zoom levels, the grid layer compresses several square glyphs of equal size. The center circle's area corresponds to the file number within the covered region, and the glyph's color denotes the average response time in the region. As the zoom level increases, the inner circle will be replaced by many small dots. Each dot represents a fire indicator to show where the indicator occurred. To help users get a quick overview of a fire station, we developed an enhanced radiant glyph. The area chart around the glyph records the quantity of rescues at the fire station in each of the six directions. The outer arc represents the number of rescues at the station, and the inner sector records the number of rescues for each time period. The spatial tempo view allows users to identify local areas within the city where firefighting resources are scarce. Our system then provides a series of interactive functions that can help users generate multiple optimization solutions. The target area panel supports selecting specific area on the map and add it to the optimization module. Then, by setting criteria and parameters on the control panel, the system activates the module to generate solutions. The results provide correlations between different criteria displayed in a matrix plot. For the candidate solutions, we use boxes in the preview window to display them. Our system also supports a what-if analysis of layout optimization solutions. In the simulation and the compression view, we introduce an enhanced line chart. Each line in the chart corresponds to a solution, and the connection points on the line represent the impact of the solution on the original layouts during the corresponding time period. When users add multiple solutions to this view, the system provides both raw mode and cloud mode. In the raw mode, user can observe the impact of one solution on the original layout over time. And in the clone mode, user can compare the different solutions horizontally at the same time period. Experts found some interesting cases through our system. The expert first observed a decreasing trend in the occurrence of fires between October and January each year and attributed this to the seasonal temperature changes. This is consistent with the spatial importance. The expert identified two areas, A1 and A2, on the map that had long response time to fires. After analyzing them individually, the expert concluded that the problem at A1 was the internal mislocation of resources, with Fire Station S1 taking on too many tasks for Fire Station S2, causing S1 to exceed its normal workload. A2 is too strained for firefighting resources due to its dense population, high degree of industrialization, and proximity to the central city. In other words, for A1, the problem can be mitigated by reallocating resources, while for A2, new fire station is required. Therefore, the expert tried to use the system to plan the location of the new fire station. After exploring and comparing, a more satisfactory solution was finally obtained. Overall, FSLens differs from previous studies on interactive VA for site location selection in several ways, including the introduction of the holistic to local perspective and the consideration of the impact of new fire stations on the original layout. Of course, our approach still has some limitations. Some come from the quality of data, and others from the requirement for real time. In the future, we hope to refine these shortcomings to help more accurate decision making.